Chapter 6, Electronic Structure of Atoms. Section 6.1, Waves. To understand the electronic structure of atoms, one must understand the nature of electromagnetic radiation. The distance between corresponding points on adjacent waves is called the wavelength, and it's given the symbol lambda. You should note that this could be between crests on the waves or between the troughs on the waves. The number of waves passing a given point per unit time is called the frequency, which is given the symbol nu. For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. Electromagnetic radiation. All electromagnetic radiation travels at the same velocity, that is the speed of light, which is abbreviated with the symbol c, and the number is 3 times 10 to the 8th meters per second. Looking at the electromagnetic radiation or the electromagnetic spectrum, you can see that the only light that we're able to visibly see is between 400 nanometers and 750 nanometers. Also, you should notice that the gamma radiation has the shortest wavelength and the highest frequency. It also has the highest energy. Gamma radiation is the type of radiation exposure that you would have if a nuclear bomb went off. At the other end of the spectrum, we have things like microwaves and radio waves, which have very long wavelengths and smaller frequencies. They also have lower energy. We have the relationship C equals lambda times nu, saying that the speed of light is equal to the wavelength times the frequency. 2 electromagnetic waves are represented below. Which wave has the higher frequency? And if one wave represents visible light and the other represents infrared radiation, which wave is which? The lower wave has a longer wavelength, that is greater distance between the peaks. The longer the wavelength, the lower the frequency by our mathematical relationship. Thus, the lower wave has the lower frequency and the upper wave has the higher frequency. Frequency is also measured in a unit called hertz or an inverse second. So when you talk about frequency, you can say how many waves per second. Obviously, the first wave at the top is going to have more waves per second or a higher frequency. The electromagnetic spectrum indicates that infrared radiation has a longer wavelength than visible light. Thus, the lower wave would be the infrared radiation. For practice, if one of the waves in the margin above represents blue light and the other red light, which is which? Looking at the electromagnetic spectrum, you should notice that blue light has a higher energy than red light. The expanded visible light portion of the electromagnetic spectrum tells you that red light has a longer wavelength than blue light. The lower wave has the longer wavelength, the lower frequency, and it would be the red light. So again, the blue light would have higher energy and the red light would have lower energy. Sample exercise 6.2, calculating frequency from wavelength. The yellow light given off by a sodium vapor lamp used for public lighting, in other words, a street lamp, has a wavelength of 589 nanometers. Notice that it is in the visible spectrum. What is the frequency of this radiation? So we are given the wavelength, lambda, of the radiation and asked to calculate its frequency, or nu. We know the mathematical relationship C is equal to lambda nu, and we can rearrange that algebraically to solve for frequency, which is equal to C divided by lambda. We take the speed of light, 3 times 10 to the 8th meters per second, divided by the wavelength, which is 589 nanometers, and automatically we see that our units are not going to be canceling out. We can't have the speed of light in meters per second and our wavelength in nanometers. That just won't work. So we convert nanometers to meters by using a conversion. Then our units will cancel out and we'll be left with inverse seconds, or hertz, 5.09 times 10 to the 14th. And again, hertz is the unit for frequency. The high frequency is reasonable because of the short wavelength. The units are proper because frequency has units of per second. Practice exercise. A laser used in eye surgery is A laser used in eye surgery to fuse detached retinas produces radiation with a wavelength of 640 nanometers. Calculate the frequency of this radiation. An FM radio station broadcasts electromagnetic radiation at a frequency of 103.4 megahertz. A megahertz is a million hertz, mega meaning 1 million. Calculate the wavelength of this radiation, making sure that your units are canceling out properly. And they also tell you that the speed of light is 2.998 times 10 to the 8th meters per second. That is to 4 significant digits.